So in this video we're going to go over how to solve a system of two equations with two unknowns using Gauss-Jordan elimination. And really all Gauss-Jordan elimination is using the ideas that we've developed over the past few videos. So the idea is, for Gauss-Jordan elimination, you put the matrix in its augmented matrix form, which we already did. You use elementary row operations to put that matrix into reduced row echelon form, and we already looked at reduced row echelon form, and we already looked at how to do elementary row operations. And step 3 is the only step we really haven't done yet, and it's really the step where you interpret the result when you get the matrix into reduced row echelon form. There's an interpretation step that comes into play. It turns out that using Gauss-Jordan elimination to solve systems of two equations and two unknowns is kind of like using a jackhammer when you need a ball peen hammer. It's too big of a tool for the job, but we want to learn it in the context of easier systems so that we can apply it to larger systems of equations. So it turns out that this technique is a nice technique to use when you have lots of unknowns, lots of variables, and it's very easy to program a computer to do it. And so we're going to learn how to do it by hand, and then ultimately what we're going to do is let the computer do it for us at the end of the day. So I'm going to advance a slide so I have a little extra space. So step 1 is just take your system and put it into matrix form. So I have a row here, the coefficient of 1 on the x, a coefficient of 2 on the y, and 9 is the constant, and then I have a negative 2 on the x. So this is the x's column, this is the y's column, this is the constants column. So it's negative 2, 1, and negative 3. And it's an augmented matrix. And then now the idea is use elementary row operations to manipulate the matrix into reduced row echelon form. And in reduced row echelon form, we need a leading 1 in the first row, and we already have that. So remember, when we have a leading 1, to have reduced row echelon form, everything in the same column has to be a 0. So I need a 0 in this position. And so I look at this and I say, hey, if I took 2 times row 1 and added it to row 2 and replaced row 2 with the result, I would have a 0 in this position, because I would have 2 times 1 is 2, 2 plus negative 2 is 0. So in a sense, we're using the elimination method. We just aren't having to keep track of the variables. So negative 2 times row 1, say what you're going to do. 2 times row 1 plus row 2, replace row 2 with the result. So I'm going to step down. I'm not doing any manipulation to the first row, so I know it's going to stay the same. And I know I'm choosing this manipulation to get a 0 into this position. 2 times 1 plus negative 2 is 0. I need a 0 in this column underneath this leading 1, or I won't have the correct form, reduced row echelon form. Now I need to go through and do the same manipulation to each of the other entries. So 2 times 2 is 4, plus 1 is 5. Replace the 1 with the 5. And finally, 2 times 9 is 18, plus negative 3 is 15. This is an augmented matrix. So I already had a leading coefficient of 1. I needed to get a 0 underneath that leading coefficient of 1. Now I look down at row 2, and I know it's not in reduced row echelon form because the first non-zero entry has to be a 1, and right now the first non-zero entry is a 5. So I ask myself, what do I need to do to get a 1 here? Well, I need to multiply row 2 times a fifth and replace row 2 with the result. So if I do that, I'm making no change to row 1. A fifth of 0 is still going to be 0. Once you get this form going, this column never changes again. 1/5 of 5 is 1, and 1/5 of 15 is 3. Now I have a leading 1 in row 2, and I need everything above and below it to be a 0, so I need to get a 0 in this position right here. But I can do that by taking and multiplying row 2 by negative 2. So negative 2 times row 2, and then add the result to row 1 and replace row 1 with that result. So notice the first column isn't going to change because I would be multiplying negative 2 times 0 is 0 plus 1 is still 1. So nothing changes here. And I'm not changing row 2 at all. I'm using row 2 to manipulate row 1 using elementary row operations. So I do negative 2 times 1 is negative 2, plus 2 is 0, and negative 2 times 5 is negative 10. I have a mistake. Where's my mistake? 1/5, a fifth of 5, oh, this should be a 3 right here. A fifth of 15 is 3. And so this is a 3. Don't make dumb mistakes. So we get negative 2 times 3 is negative 6, and then negative 6 plus 9 is a 3. And when I look at this now, I'm in reduced row echelon form. Each row has a leading 1. That's to the right of the previous row's leading 1. If I have a leading 1, everything in the same column is a 0. So once I get it into reduced row echelon form, which I have right here, I want to interpret the result. And what I need to remember is that this is the x column and this is the y column. So if I think about what this is saying that 1x, I'll write this in a way that we usually don't, 1x plus 0y equals 3. Well, we usually wouldn't put a coefficient of 1 on the variable, and if it's 0y's, we would just usually say, hey, x is equal to 3. And here this is saying 0x's plus 1y equals 3, which is the same as just saying y is equal to 3. So the solution then is the ordered pair 3, 3. So this is a case where we have two lines that intersect in a single point, and we're able to interpret that from the reduced row echelon form of the matrix.